Hey there, hi there, ho there. Welcome back to Unit 2. So Unit 1, just a little introduction on natural hazards. So now we're going to just start talking about the Earth and why some of these hazards occur. And we're going to work from the inside out. We're not going to talk about Earth's formation. I do that in some of my other classes. But we'll kind of look at inside out and see how what's going on the inside may affect geology and the presence of hazard on the surface of Earth. So that's why we're talking about Earth's internal processes here in Unit 2. So what is the inner structure of Earth? That's Section 1. Well, it's made up of a few different layers. You have a crust, a mantle, an outer core, and an inner core. Crust, mantle, outer core, inner core. All right? So let's see. So we have the crust. There's two types of crust. There's oceanic crust or continental crust. Easy way to remember is that if you're standing on dry land, that's probably continental crust. And if you're in a boat in the ocean, underneath all that water is probably oceanic crust. Not always, but for the most part, that's how it kind of works out. Oceanic crust is thinner, only about 3 to 5 miles thick. Continental crust thicker, 5 to 25 miles thick. But oceanic crust is more dense. It's more compact, so it's kind of heavier. Continental crust, while thicker, it's less dense. It's not as compact. So oceanic crust kind of sinks, while continental crust kind of rises. But in any case, the crust is solid. Now we're talking about ignoring the ocean. Underneath the ocean is solid crust. But there's two different types. And then below the crust, and so again, the crust is very, very thin. Sorry, to go back. The crust is what we're on is just a very thin shell of the Earth. Then right below the crust, you have the mantle. It is mostly solid. It kind of flows with the consistency of Play-Doh mixed with rocks. It does move, but it's mostly solid. But again, it kind of moves. Imagine hot Play-Doh mixed with rocks. You can kind of move Play-Doh around, so it does flow a bit. There is some movement, very slow movement within the mantle. But again, it's mostly solid, about 1,800 miles thick. It's the biggest layer by volume of Earth. Then we have the liquid outer core, which is about 1,400 miles thick. And it's made up of mostly iron, which is Fe is the chemical symbol for iron, and nickel, Ni. So the outer core is made of mostly iron and nickel in a liquid state. So in a purely liquid state. How we know that, a little bit later. And then we have the solid inner core, about 800 miles in radii. Again, also iron and nickel, but in a solid state. So solid metal inner core, liquid outer core, thick mantle, very thin, which is mostly solid, and then a solid crust. You've probably seen all the movies. Well, maybe not. Maybe you have seen a movie or two about where people try to go to the center of the Earth and it gets so hot and what they're trying to get through. Yeah, that's a little science fiction, but it is true that the further down you go on the Earth, the hotter it gets. Why is that? Why is that the case? Why is the center of the Earth so hot? That's an important aspect of what's helping to create hazards on the crust. Well, it comes from a couple of different places. First, heat from or energy from Earth's formation. So when Earth formed, kind of an image here you see here on the right. So when Earth first formed, it formed from a bunch of stuff out in space kind of coming together. So stuff kept bombarding and smacking into Earth. That's how all the planets and our star, the sun, and all stars form. Kind of material starting to collect. Well, when things were hitting that velocity, the speed of these objects as they hit, the Earth, created friction, created heat. So the Earth was so large, and this bombardment process happened for so long, that the Earth was initially, when it formed, a hot, molten, liquid rock ball, a big ball of lava floating out there in space. Then you got the outer stuff cooled, so the crust cooled down, but that inner core, the inside of the Earth, remained hot. So even 4.54 billion years after the Earth formed, some of that original energy in the form of heat from Earth's formation is still kind of trapped. So one reason the center of the Earth is so hot is leftover energy, leftover heat. Another one is radioactive decay. Now, the inner core isn't only solid iron and nickel. The outer core isn't only liquid iron and nickel. Not only there, but in the mantle as well. There's other stuff. It's for instance, the core is mostly iron and nickel, but there's other stuff as well. So even in the mantle, there's a bunch of other stuff. Some of that other stuff is radioactive material. When radioactive material decays, which means it naturally just starts to break down, it happens at the atomic level. So a little chemistry, I guess. So you get what's known as a parent isotope. It undergoes radioactive decay. It just starts to split. And what happens, it creates what's called a daughter isotope or a daughter product. And then it also releases energy in the form of heat. So in that radioactive decay process, as it's decaying from one thing to the next, heat is released. So you have enough of this radioactive material, which is typically heavy, that when Earth formed, the heavy stuff kind of sank towards the center. The lighter stuff kind of stayed towards the surface, the crust. The crust is the lighter stuff, by the way. But this radioactive stuff you can find it throughout layers of Earth, but since it's typically heavier atoms, a lot of that sunk towards the center, undergoing radioactive decay, also providing heat. So a couple of different places. So the Earth is hot because of leftover energy in the form of heat and radioactive decay. So so we got some heat in there. So what happens to all the heated material inside the Earth? Does it move, or does it just stay in place? Think about a hot air balloon. Those big balloons sometimes you see in the sky. It's not a cold air balloon, it's a hot air balloon. Because what do hot air balloons do? Well, when you heat up the air in the balloon, it rises. Hot air in general rises. Cold air sinks. The reason being is because hot air is less dense. Think of it as lighter than cold air. Cold air is more compact, more dense, heavier. So when you have something that has a lower versus a higher density, the higher density stuff sinks, the lower density stuff goes up. So hot air, since it's less dense, will rise. Cold air sinks. That's why a hot air balloon goes up and goes down when the air starts to cool. That process happens in a number of different things. I don't know if you have one of these in your home, a lava lamp, kind of the same process. Heated material goes up, cools down, sinks back down. That same process is going on within the Earth. A lot of it happens in the mantle. It happens in some of the other places, but there is a process in the mantle, the layer just below the crust, called mantle convection, where heat provided from the core heats up material. That material rises, it cools down, and it sinks. And that process happens all over again. That material, once it's heated up, rises again, gets further away from the energy source, so it cools down, it sinks. It's called convection. It's called convection. When hot air rises and then cold air sinks, that's convection. So this is a cross section of the Earth. So you have the solid inner core, the hottest part of the Earth, conducting heat to the liquid outer core. There's some convection going on there because the liquid outer core does move. And then the liquid outer core transfers that heat to the mantle, where mantle convection occurs. That hot material rising, cool. As that material gets further away from the core, it's further away from the heat source, so it'll cool down, so it'll sink. Gets closer to the core, heats up, cools down, sinks. So that's why I say the mantle is mostly solid, because if it was totally solid, it wouldn't have this movement to it. The hot Play-Doh mixed with rocks does slowly move and slowly fall. That heat is what and the heat drives the movement of the mantle, and that movement of mantle material helps to drive the overlying plates, the overlying crust of the Earth. It breaks up the plates. It moves the plates around in something called plate tectonics. Whatever heat is transferred to the crust, and that heat from the crust then is transferred into space. which is actually by that point not a lot. Same thing happens in a boiling pot of water. When you put a pot of water on the stove, the hot water rises. As that water gets further away from the bottom of the pot, where the heat is, it cools down, it sinks. That's why if you've done any cooking, some instructions say a rolling boil, because the water's kind of rolling around in there. So again, this is a little closer snapshot of the crust and the mantle. That hot rock material begins to rise. As it cools down, it begins to sink in a convection cell. But again, mantle material, imagine hot Play-Doh with rocks. It's very sticky and it moves very slow. So it's very sticky stuff, Play-Doh and rocks. So as that mantle material rises and encounters these overlying crusts, these overlying plates, as that mantle material rises and kind of makes its way off, it kind of starts to pull on the crust and break it apart and start to move the crust, move these large plates of earth. So it kind of either moves them apart, or depending on where these convection cells are in the mantle, it might crash other crust or plates together. So how do we know the Earth's plates have moved? The Earth's crust is broken up into a number of different plates, about 12 or 15 big plates and a bunch of small ones. It's not just a one solid shell that the crust is. It's broken up because of mantle convection. But how do we know the Earth's plates have moved? How do we know they're continuing to move now? This process, the mantle moves very slow, therefore the crust and the plates moves very slow. So, but how do we know that? I don't feel it. I don't feel like what I'm on is moving around, but it is. I can't see the whole giant continent of North America moving around, but it is. So how do we know that? How do we know that happened in the past? How do we know that's happening now? Well, we need some proof. And that's what we're going to find out in the next section. So I'll see you back here in just a second.